यूनिवर्सिटी ऑफ इंजीनियरिंग एंड मैनेजमेंट का क्रेज लगातार बढ़ता जा रहा है। स्टूडेंट्स के लिए 100% प्लेसमेंट और उत्कृष्ट परिणाम देने वाले यूईएम मैनेजमेंट ने अपनी अलग पहचान बनाई है। यूईएम के रोबोटिक मॉडल्स, जॉब फेयर्स, स्पोर्ट्स एक्टिविटी, क्रिएटिव प्रोग्राम्स आदि स्टूडेंट्स को अट्रैक्ट कर रहे हैं। पेश है एक रिपोर्ट। जयपुर स्थित जेके के परिसर में माई एफएम द्वारा आयोजित फेयर में यूनिवर्सिटी ऑफ इंजीनियरिंग एंड मैनेजमेंट का जबरदस्त क्रेज देखने को मिला। यूईएम के स्टॉल को लेकर विजिटर्स में भी खासा उत्साह देखने को मिला। तो वहीं यूईएम के प्रबंधन ने भी यूनिवर्सिटी की एक्टिविटीज, एजुकेशन सिस्टम, फैकल्टी, इंफ्रास्ट्रक्चर, हॉस्टल सुविधा आदि से संबंधित सभी जानकारियां विस्तार से उपलब्ध करवाने के लिए पर्याप्त स्टाफ की तैनाती की।
माई एफएम की तरफ से जो है इस कार्यक्रम का आयोजन किया गया है और यूनिवर्सिटी ऑफ इंजीनियरिंग मैनेजमेंट ने भी यहाँ पे पार्टिसिपेट किया है। स्टूडेंट्स ने यहाँ पे आके अपने कोर्सेज के बारे में जो है इंक्वायरीज की है, हमने उनको सेटिस्फाई भी किया है, उनको समझाया है कि उनके लिए कौन सा कोर्स बेटर है। इसी के साथ में यूईएम के स्टूडेंट्स ने जो प्रोजेक्ट्स यहाँ पे डेवलप किए हैं वो भी लर्निंग जो उनके अंदर और एक्सपीरियंस जो उनके अंदर यहाँ पे लगाए गए हैं और स्टूडेंट्स को हम मोटिवेट कर रहे हैं कि वो यूईएम ज्वाइन करें और ऐसे प्रोजेक्ट्स जो हमारे प्रीवियस स्टूडेंट्स ने यहाँ पे बनाए हैं वैसे प्रोजेक्ट्स वो बनाएं।
इस इनोवेशन में हमारे काफ़ी सारे प्रोजेक्ट्स हैं। इसमें IoT बेस्ड हमारे प्रोजेक्ट हैं, AIML के प्रोजेक्ट्स हैं और साथ में हमारा AIML के साथ में मशीन लर्निंग के प्रोजेक्ट्स तो हमने ऑलरेडी एग्जीबिशन में लगा रखे हैं, क्योंकि इनके बेसिस पे हमारे स्टूडेंट को काफ़ी प्लेसमेंट मिला है। जैसे हमारा टेस्ट पैक का है, रिसेंटली हमारे 400+ कंपनीज के साथ MOU है जिनके हमारे सारे बच्चे प्लेस्ड है, जिनमें हमारा हाईएस्ट बीटेक का प्लेसमेंट 33 लाख का था। ऑन एन एवरेज हमारा बीटेक का प्लेसमेंट 7.5 लाख का था और हम लास्ट विलिंग कैंडिडेट तक हमारे बच्चों का प्लेसमेंट करवाते हैं। अभी भी हमारे 3rd ईयर में जो स्टूडेंट है जो 4th ईयर में अभी गए हैं उनमें से मैक्सिमम 40% स्टूडेंट ऑलरेडी प्लेस्ड हो चुके हैं। वो बीटेक के, BCA और BBA के कैंडिडेट हैं और हम हर एक बच्चे के लिए कंटिन्यू नई नई टेक्नोलॉजी का यूज़ कर रहे हैं। रिसेंटली काफ़ी सारे अपडेट किए हमने कोर्सेज में। अपार्ट फ्रॉम दैट टेक्नोलॉजी में हमने AI की लैब इस्टेब्लिश की है, IoT की वर्कशॉप्स करवाई है।
अलग अलग इनोवेशंस और क्रिएटिविटी के लिए पहचान बनाने वाले यूईएम के स्टूडेंट्स ने भी अपने अपने क्रिएटिव आइडियाज से विजिटर्स को अवगत करवाया। यूईएम के स्टूडेंट्स ने रोबोटिक मॉडल्स की प्रदर्शनी भी लगाई। इसके साथ ही स्टूडेंट्स ने रोबोट मॉडल्स की कार्य प्रणाली, ऑपरेटिंग सिस्टम, इनोवेटिव आइडियाज आदि के बारे में भी विस्तार से जानकारी साझा की। आइए आपको सुनाते हैं क्या कुछ कहा यूईएम के स्टूडेंट्स ने।
ये हमने रोबोट बनाया है 3D प्रिंटेड माइक्रो ह्यूमन वॉकर, जिसका IP एड्रेस ट्रैक करके आप अपने फ़ोन से वाईफाई से कनेक्ट करके एंड यू कैन ऑपरेट इट फ्रॉम देयर इटसेल्फ। लाइक यू कैन सी इसमें हमने कुछ कमांड्स दे रखे हैं और उस कमांड के हिसाब से वी कैन मेक इट वर्क।
एक आर्डुइनो का स्मार्ट स्पाइडर रोबोट है जिसके अंदर हमने आर्डुइनो के अंदर कोड करा है, जो कि हार्डवेयर प्रोग्रामिंग है। उसके अंदर हमने कोड करके मोटर के साथ कनेक्शन करके एक स्पाइडर रोबोट बनाया है जो कि ऑटोमेटिकली वर्क करता है और किसी भी सरफेस पे ये वर्क कर सकता है। ये कोई भी सरफेस हो, रफ, स्मूथ, कैसा भी सरफेस हो, ये इस पे ऑटोमेटिकली वॉक कर लेता है। चाहे कितने भी ऊपर नीचे, ये नॉर्मली अपस्टेयर डाउनस्टेयर उन पे भी वॉक कर सकता है।
वी हैव मेड दिस रोबोटिक हैंड which is used for the handicaps. It works like our brain transmit the signal and through this Arduino अगर we can use and through hand it emits and then it works.
ये एक स्मार्ट डोर लॉक, ये आप दुनिया के कहीं भी रहो, ये आप अपनी फ़ोन के एक सॉफ्टवेयर से हमें सॉफ्टवेयर ही बनाया है, ऐप भी बनाया है एक, तो आप इससे कनेक्ट करके तो इसको दुनिया के कहीं भी रहो इसको चला सकते हो। ये आपके घर की सिक्योरिटी के लिए बनाया है हमने। अभी इसमें अलार्म भी लगाएंगे, ये सिर्फ प्रोटोटाइप है, इसमें अलार्म भी लगाएंगे तो क्या होगा, जिसमें ये ऐप है तो अगर कोई आपसे डोर से छेड़खानी करे या कोई भी कुछ करे तो क्या होगा, आपकी जिस डिवाइस में ये ऐप है सब में अलार्म बज जाएगा और आपके घर में तो बजेगा ही।
हमने एक ये गेमिंग डिवाइस बनाया है, इसमें एक स्नेक गेम इंस्टॉल किया गया है एज ए प्रोटोटाइप एंड ये एक मैट्रिक्स डिस्प्ले जिस पे हम स्नेक गेम खेल सकते हैं विद दिस कंट्रोलर्स। अप टू 500 गेम्स हम ये डिवाइस में डाल सकते हैं एंड इट कैन बी कन्वर्टेड टू अ पॉकेट साइज डिवाइस एंड इट इज़ बेसिकली फॉर 10 years किड्स एंड वेरी प्रॉफिटेबल फॉर पेरेंट्स इफ दे बाय इट। हम और हमारी टीम ने एक रोबोट स्पाइडर बनाया 3D प्रिंटेड। ये हमारे कॉलेज के अंदर ही पूरा प्रिंटेड हुआ है, तो 3D प्रिंटर से प्रिंटेड हुआ है। ये रोबोट हम एक ऐप के द्वारा कनेक्ट कर सकते हैं, IP एड्रेस के द्वारा। ये इसका ऐप है, ये हम लोगों ने मॉडिफाई किया है ऐप को
और इस ऐप के अंदर ये जो फंक्शन है, इस फंक्शन को दबा के हम लोग इसको चालना भी कर सकते हैं।
बहरहाल एडमिशन प्रक्रिया के साथ यूईएम में शैक्षणिक सत्र की भी शुरुआत हो चुकी है। यूईएम कैंपस में नए स्टूडेंट्स के लिए यूनिवर्सिटी की लैब्स और हॉस्टल के साथ ही एकेडमिक इंफ्रास्ट्रक्चर स्टूडेंट्स को लुभा रहा है। जयपुर से आशीष तिवारी की रिपोर्ट।
जय हिंद पेरेंट्स, क्या आप ये दो फ्रैक्शन देख के मुझे बता सकते हैं क्या है? मैं आपको एक ट्रिक से
Am I audible? Good afternoon, all. Today is the fifth day of our MDP, Advanced Tools and Techniques for Scientific Writing and Publication. On the fifth day, we are just going to start our session. The topic of the session is Advanced Computation Techniques through MATLAB software. The today's speaker is Dr. Shika Samuel from Nigeria. Uh, Professor Shika Samuel is an assistant professor in Department of Mathematics, Taraba State University, Jalingo, Nigeria. He his expertise in mathematical modeling, fraction calculus, bio-inspired algorithm. He is skilled in computation techniques also, including MATLAB, Maple, Mathematica, and other softwares. So I welcome you, Professor Shika Samuel, to deliver a talk on the fifth day of FDP. Professor Shika, are you there? Hello.
Hello, can you hear me? Hello,
Yes,
good
yes,
morning.
yes, you are audible.
Hello.
Yes, audible. You are audible.
Okay. Thank you very much. Let me try to share my screen here. I will turn to the laptop. One moment from me here.
Okay.
I welcome everyone. Let me just try to share my screen here. It's okay.
Sir.
Yes, can you hear me?
Sir, I request you to please switch on your video camera so that every participant can see you.
Okay. I want to sign in with the laptop.
No issues, sir. Take your time. Take your time. No issues.
Okay. It's all right. I hope you can see me now. Hello, can you see me now?
Yes, sir.
Share my screen with you. Hello, can you hear me, please?
No, the screen is not visible.
Please, you need to activate my device so that I can share my screen.
No, you can share. You have been given all the options. Don't worry. You can share it.
Okay, you say host disabled participant screen sharing.
You are not host. You are co-host.
Okay.
You are able to open. Please, I request you to please open your camera so that I can check the other technical issues.
Dear participants, just wait 1 or 2 minutes. I think there is some technical issue with the speaker, so he will be joining very soon, within 1 or 2 minutes. Have patience. Please wait.
Hello, can you hear me?
Yes, yes, you are audible and visible both.
Okay, it's all right. Can I share my screen now with you?
Yes, please share it.
Okay. Can you see my screen?
Yes, it's visible.
It's all right. Please, I want to apologize for the mix-up. There's some technical issues from Zoom, and please, my apologies, please. Can I continue?
Yes, everything is fine. You may proceed.
Okay, it's all right. So I want to start by appreciating every one of us, the participants, and the Vice Chancellor, the department, the team, the convener, for this opportunity to be part of this program. I want to proceed with the talk in earnest. And first of all, I'll be talking about numerical computing techniques.
Sir,
Engineers, can you hear me?
Sir, sorry for interrupting, but your voice is not clear. Your voice is continuously cracking.
Hello, can you hear me now?
Yes, now it's clear.
It's okay.
Yes, please.
I said I'll continue the topic, numerical quantification techniques for scientists and engineering. And I will start with an overview of what MATLAB is. And so MATLAB, I don't know whether all of us are familiar with MATLAB, but at least a number of scientists know what MATLAB is. And it is a programming language and numeric computing environment.
Sir, sorry again to disturb you. Actually, the voice is regularly disturbing. Actually, I would request, if possible, please use some earphone or some earbuds. Actually, there is some issue actually in the voice.
Hello? Hello,
Yes,
can
yes, please start.
okay, it's clear, isn't it?
Yeah.
Okay, sorry. You know, there is differences in accents, but so I'll continue with the talk.
Yes, please.
What I want to do first is to look at the highlights on MATLAB, and the MATLAB is a programming language and it has a lot of computation capacity, and I want to focus on one or two of them in this talk today because of the time. So I will be looking at the ordinary differential equations, fractional ordinary differential equations, and partial differential equations with respect to computation in MATLAB. Can you hear me? Hello?
Yes.
Okay. So can you see my screen?
Yes, it's visible.
It's all right. So I want to say that MATLAB has so many computing capacity, and in this talk, I will be looking at a few of them. So we'll be looking at a few of them. So I will first of all look at what is mathematical modeling. It is a valuable scientific tool, and its applications are very much, and it gives precision and strategy for problem solving and enables a systemic understanding of the model or the environment or whatsoever we're modeling. So it also allows better design, control of system, and effective use of model computing capabilities. So mathematical modeling has been classified. I will not go into details, but we have the linear, the non-linear, have static, have the dynamic, have discrete and continuous, deterministic and probabilistic or stochastic. We have inductive, and floating, have strategic and non-strategic modeling. So I want to go into a particular aspect of modeling, which has to do with fractional differential equations. And I want to say that fractional differential equations are very powerful because they make us to understand non-locality and spatial heterogeneity of systems. The history, systems that depends on the history, and because of the complexity of the medium or the media we are looking at, sometimes the integer order differential equations may not be able to describe the system properly. So here I want to take a look at quickly the definition of some of the terms, which is Riemann fractional integrals and differential derivatives, which is defined as an expression which is taken from or was a generalization of n-fold integration, and is given here, as you can see. And then we have the fractional derivative, which is also given here. So we also have another one called Caputo derivative, which is also useful and is one of the most useful fractional differential operator, because It's very consistent with initial value problems. It's very consistent with the initial value problems. And then we have grown words and it's also defined in discrete form, and it's very useful if you want to approximate fractional differential equations. So this is just to give us an overview. So if you have a differential equation, fractional ordinary differential equation, and you want to approximate, the basic thing that you see is that you have to employ the Grunwald's derivative to approximate it, and it will give you an approximation of what the derivative is all about. And if you want to approximate, there is what is very important called the memory length. And this is the reason why the fractional ordinary differential equations are difficult to compute, because you have to take along the history from the beginning. So they are not just being computed the way the integer order equations are computed. And because of that, we have a technique that is being used to compute the ordinary differential equations using this particular operator, which is called Grunwald operator. So as I go on, I think we'll look at one or two of them. I will just give you an overview, then I will go to MATLAB so that I may not need to come back here so frequent. So I'm just trying to give an overview or a picture of possibly what we are going to look at in MATLAB practically. And I use this because I want to speak on fractional ordinary differential equation and partial differential equations because the applications are much. And if you couple with other techniques like machine learning, other algorithms, parameter estimations are very easy and accurate. So that's the reason why I want us to look at it together in this talk. So having said that, I want to go to MATLAB to take a look at one or two things there, just to give us highlight before we go into the applications. And a moment, let me switch over to MATLAB to the other components. Okay. One moment, let me switch over to MATLAB. Okay, very good. Now, very good. Now, if you look at MATLAB, can you see my screen? Hello, sir.
No, it's not visible right now.
Okay. A moment. Yes. Can you see it now? Can you see?
Yeah, presentation is visible.
All right, it's okay. So, well, I wanted to apply a number of equations, famous equations, to illustrate what I'm saying. And one of them is the fractional order Lorentz system. All of us are familiar with this system, at least majority of us that are mathematicians are familiar with this system. And the fractional order is gotten from the integer order by replacing the derivatives with fractional derivatives. And then we got a system. And in the case of this system, we have the orders Q1, Q2, and Q3, which are ordered depending on the equation. We have equation 1, 2, and 3. Then it means we have Q1, Q2, and Q3. And then on the right-hand side, we have the variables and the parameters here. And this system has equilibrium points, 3 of them. We have E1, which is the trivial, the obvious. And then we have E2. And then we have the E3, which is here. And if we want to look at the stability of the system, the first thing we do is to get the Jacobian. And when we get the Jacobian, because we already had the values of the parameters here, the constants here, we have rho here, we have sigma, we have beta, all of them are given. So we're able to compute the equilibrium points, and then we took the Jacobian of the matrix to see whether the system will be stable. But this is also, it's not to say that we cannot go into details of other analysis that has to do with them, but because we have limited time, we are trying to restrict ourselves to a number of things that we can get ourselves acquainted to. So in this case, we use the Greenwald definition of derivatives, which is this, to discretize the system. The system here. And then this component here that we're seeing here is what is called the history part or the memory part. It has to say that this system entirely is depending on a history. And the dynamics of the system is being altered by the history or the past events. And so that is the reason why you see sigma, the sum from J equals to V to K, that is from the memory length. You now begin to evaluate the history of each and every one of the equations. You can see the first equation has its own, the second equation has its own, and the third equation has its own. Another point I want to make before we go on is that if you look at this, we have two components. One is the binomial coefficients. The binomial coefficients are here. And then from initial point, we have the value is equal to 1. And then from there, we'll calculate depending on the value of j, and also depending on the value of the order or the fractional order. So these binomial coefficients are computed, and the computation is very accurate. So if we do that, the system brings out a lot of beauty. There are so many beautiful things that this system shows. Well, I want to go to MATLAB there to look at one or two things before we proceed. Can you hear me clearly?
Yeah, no issue. But there is some black spot on your screen actually. I hope there is might be some network issue.
Okay, but okay, can you see it now?
Yeah, it's still there.
You said there's a blackout?
Yeah, this one.
Okay, it means okay. Is it out now?
Nah, it's yeah, it's removed now.
Okay,
Please,
it's
please proceed.
because
Yeah.
you made me admin, so the thing is reflecting on my screen here.
Okay.
So let me go back to the MATLAB and try to share it so that we can do one or two things. Okay, very good. Now, one moment from here. Okay. Okay. It's all right. Okay.
Professor Shika, your MATLAB screen is not visible.
Okay, I'm trying to.
Yeah, please open it and share it.
I should do what?
Dear participants, please wait few moments. Actually, he is presenting from Nigeria. So I hope there might be some technical issues and some glitches. So he's trying to present his MATLAB screen. So please wait a moment.
Hello?
Hello, Professor Shika, are you able to solve the problem?
Yeah, I'm trying to get this. The screen is trying to give some, but I will resolve it immediately. Just
Please,
Professor Shika, are you there? Professor Samuel Shika, are you there? Can you hear me?
Hello, Professor Samuel Sika, are you there?
Hello?
Yes, you are.
Hello?
Yes, you are audible. Please start the session. Please, please.
Okay, okay. Please, it's all right. MATLAB
Yeah,
is here.
you have
Right.
you have given all the rights. Please start. Yeah, now it's
Okay.
visible. Now it's fine.
Okay. Can you see the MATLAB now?
Yeah, it's absolutely fine. Please start.
It's all right. Please, as we're discussing, this is the solution of the system, and I will try to plot it. I will try to plot it here now. Jesus Christ. And let me just comment this one there. I will plot the rest. Can you see it now?
Your MATLAB screen is visible. No issue.
Okay.
Command window is showing actually.
Okay, it's all right. So as you can see, I want to show you the no, the system is freezing. I don't know. Please, can you change? Just make me a guest. Let me not be an admin because the participants are disrupting the presentation. Can you hear me?
You have
Hello?
been actually you have given the co-host permissions. No issue. So you have all the authorities.
It's making the system to freeze.
Your presentation is not visible actually now. Please share your screen. Professor Samuel, please share your screen.
Okay. The thing is causing the system to freeze. Can you hear me?
Yes, you are audible. Please proceed. It's visible.
Okay. No, I'm not sorry. Professor Samuel, you are visible, but your screen is not visible yet. Professor Samuel, can you hear me? Participants, we apologize for this because there is some technical issue in Nigeria, I think, and that's why again and again we are getting problem. So have patience. Please wait for a while. Professor Samuel, can you hear me?
Professor Samuel, your screen is visible.
But you are not audible, Professor Samuel, you are not audible at all. Are you there?
Yes, can you hear me now?
Now you are audible.
Can you hear me, sir?
Your screen is visible, you are audible.
Okay. Sorry, the MATLAB is heavy. The packages are heavy, so the system is trying to malfunction. So let me just go on with the presentation. I'll give some little highlights, and then at the end, I will do the practical aspect of it. Can I proceed?
Yeah, please continue.
Okay, it's all right. So I was trying to explain. So this is when you plot the system. This is this is the graph you see, and if you change the value of if you change the values of Q, Q1, Q2, and Q3, you will have something different from the plot we have here because of the order of the differential equations is also affecting the behavior of the system. So the behavior of the system depends not only on other parameters, but also on the fractional order parameters also. So this is also a plot from there, as you can see, is a chaotic kind of system. So in this case, I also want to show another system, which is fractional nodal system. It has, this is the integer order. You can see these are the equilibrium points, E1, E2, and E3. Can you hear me? Hello, can you hear me?
Yes, you are audible, no issue.
Okay, it's all right. So you can see this is E1, E2, and E3, and the Jacobian matrix is here. The eigenvalues, the eigenvectors are also shown here, the system. And I had wanted us to plot and see exactly the behavior of the system, but because the MATLAB is giving a little challenge, I will postpone it. I will go to the end of the presentation, and then I will do the practical aspect of it from where we have started. So I will go to another system. This is actually the extended another system with parameters Q1, Q2, and Q3. The numerical scheme also is here, you can see. And the system is also very good. You can see if you make a plot, this is what it will show. And if you change Q1, Q2, and Q3 from the codes, you have a very beautiful system also. And then another system here is one of the most beautiful systems, the Volta system. And it has the integer order, equation 1, equation 2, and equation 3. And then this is the plot. You can see the plot is very beautiful. And you can change that system or generalize it to the system of fractional order. It gives this kind of chaotic situation or plots. And if you extend it to fractional order, like we have said, you can see that you will have Q1, Q2, and Q3. Once you vary any of them, you will have another plot. So this is the Jacobian matrix of the Volta system. And the numerical scheme for it is also here. You can see question 1, 2, 3, and 4. And then we have this system. So these systems are very, very important because you can apply them in other fields like disease modeling. You can apply them in other systems like control systems, in electric systems, other mechanical systems that has complexities. You apply them. This is just a template for us, for PhD students or for researchers to look at it. There are some areas that we need to use these systems as a template to investigate and check how this can be applied in that particular area. Are you hearing me? Hello?
No problem, Professor. Please proceed.
Okay, very good. So I was trying to say that you can use this system. Is one of the most important aspects of modeling. You can use the system, any of the templates, the codes, the MATLAB codes. I will share it with the convener. Anybody that wants to reproduce research in this area, or anybody that wants to do another research, the codes are there. They are simplified. They run very fast. I took it from some of my collaborators, and the system can give us a true picture of what the dynamics of any mathematical modeling or models will look like. So you can see how beautiful this particular one is, and then you can apply it as well in other systems, financial systems, stock markets, and any other aspect also. So I want to go to fractional order. Fractional order PDEs, they are very important also because the applications are much or are many.
Professor Sample,
Yes.
please use slideshow presentation mode. Please use it.
Sir?
Please use slideshow presentation mode.
Okay. Is it good now?
Yeah, it's good now.
Oh, it's all right.
Good. Yes, good to go.
Can you see clearly now?
Yes.
Very good. So I'm saying that I want to go to fractional partial differential equations. The applications are many, but we find it very difficult to compute them because of the complexities using other standard computational algorithms like finite difference method, finite element methods also. So in this presentation, I want to look at a particular technique that is very, very effective and easy to try methods, which is attractive, and it can be coded easily. So we have the advantage is that every the codes can be simplified. Anybody can read the codes, and the accuracy is very high compared to other techniques. So in this case, I want to look at the spectral method the operator is given by this. You can see this is a normal Laplace operator. You can see these are the eigenvalues. And then these can be extended to a fractional order Laplace operator. And see these are the eigenvalues you can see here. So it's very easy for researchers to, once you have computed this, it's very easy to extend it to fractional order operator. So I will look at that quickly. If you look at it from here, you can see that we took an example of a heat equation. You can see the equation is given as you can see this is the fractional, the time derivative, and this is the fractional in space operator here. You can see, and the subject to this initial conditions. So if you look at this equation, you can discretize it. You take a Fourier transform. Once you do that, you can collect the solution, and the solution is given based on, it depends on the initial conditions. You can see the initial conditions here, the codes, it will give a different it's a different solution if you have a homogeneous boundary conditions. If you have otherwise non-homogeneous, it will still give you a different solution. So the advantage is that this can be coded easily, and the applications, like I've said, are mathematical biology, ecology, physics, chemistry, and many other mathematical patterns and phenomena for special cases. So this is how it looks like this equation that I've shown here. We took this equation and then we took the Fourier transform of that equation. Then after that, it means this component has been dealt with. This is the component that came with the Laplace. So instead, we have this expression here, which is called the eigenvalues. The eigenvalues are here. So, and then the other component is also expressed in terms of the Fourier transform. So if you do that, like I've said, you now get the solution. You have removed the linear parts of the equation, and then you now apply the integrating factors on both sides of the equation of the solution. You can see from here. So you can see U is here. So we now apply. When we do that and you differentiate, it will give you this expression here. And with this, it's very easy for us to use the discrete fast Fourier transform to solve. So in this case, be able to now transform this equation into this particular equation into system of ordinary differential equations. Instead of partial differential equation, it has been transformed into ordinary differential equations. Are we together? Can you hear me? Hello,
Professor, there is no problem. Please continue.
Okay. So, like I've said, if you use that, then you will be able to transform the partial differential equation into ordinary differential equation. And then we use the well-known Range-Kutta methods to now solve the equation. So this is the famous Range-Kutta method, which is given as this. And then we use that to discretize or to solve our system of ordinary differential equation, which was converted. You can see it in this equation here. And then this is equation with respect to u, this is v. And then you can see that we have modified it into u mu I and then vi. So these equations are very easy to code because we are using the Ranjikuta method to solve the ordinary differential equation. You can see the way we have discretized it. And this entirely we are going to use, if it's for a MATLAB, luckily we have this FFT is meant for one dimension. And then this is the inverse fast Fourier transform. This FFT2 is the two-dimension fast Fourier transform, and this is the inverse. So we have used what is called exponential time differencing to discretize that system, which the system is categorized. I'm making reference to this particular system is categorized into a linear and non-linear components. So because of that, we can now take the Ranjikuta methods, and this is the scheme that's given to us. This is a well-known scheme, a famous scheme in literature, and these are the coefficients of the Ranjikuta system. All these are coefficients, are components of the Ranjikuta scheme. So we are going to apply this system in two aspects, two systems. The system number one is the Scott equation. And then system number two is this particular equation. So I will have to revert back to MATLAB to see whether it can work well now, so that we can do some practicals. Okay. Okay. So here, I was able to run the system. Like I've said, let me start with the partial differential equations, one that we just finished now. I'll go back to the other one later. The first equation is this. These are the parameters. Can you see the screen? Hello, sir?
Yes, it's visible.
Okay, it's all right. So these are the parameters of the system. And then this is the fractional parameter, is here, alpha. And then these are also the parameters. Here, this is the grid. This is the grid. And then this is initial conditions. So in the initial conditions, you can see that here we want to take the Laplace, the first Fourier transform here of all of them. First Fourier transform. And then after that, we want to pre-assign it so that the MATLAB will be very fast. So here we pre-assign the system. And then here, because we have the grid here, we have to turn it into a mesh grid because it's a two-dimensional system. You can see two-dimensional system here. And then this component is the most important part of the algorithm. This small code you have seen here, I don't know whether I'll have to zoom it. Well, but it's the most important part of this algorithm because this is where you can scale it to fractional parts. You can scale this to 3 dimensions. If it's 3 dimensions, if you have X, Y, Z components, you can just extend it here without any problem. You just extend it to KZZ from here. That's all. So the algorithm is very useful because if you want to extend it to 3 dimensions, it's very easy. And then if you want to extend it to fractional component, it's very easy. All that you need to do here is to change alpha to any value that you think or you want to evaluate. So if alpha is equal to 2, then it means that the system is only it's a normal system, it's not a fractional system. But if alpha is not 2, then it is a fractional system. Then after that, these are coefficients. Then the coefficients, after coefficients, we try to code the exponential time differencing scheme, that is Range-Kutag scheme here. Then after that, this, we are just trying to code it to reduce the codes, make it compact there. And then here we have to run the iterations from n equals to 1 to n equals to the final time. You can see. So then the last component here is very important. I want everybody to pay attention. This point is because we save the computations that we do here because it takes a long time to process some of these computations. So instead of computing it over and over again, like in this presentation, it will take like 5 to 6 minutes before it will finish. So all that I did was to save it. I'll compute and then save it so that the result can be loaded in MATLAB. So you use the save command, and then you use the file name that you want to save it, then .mat is very important. Then the variables that you want to save. These are the variables that you want to save. You can see we save the time, we save U, we save V, we save N, we save L, we save X, we save Y. All these variables, we save them. So this function is for initial conditions. This component is for the right-hand side of the system. And this one is just to service a routine, make the code very fast. So with this, I was able to compute it yesterday, or today, sorry. And what I will need to do here is to load it. I will load the system. I will load what I have computed. I computed in 3 different levels of alpha. Alpha when alpha is 2, when alpha is 1.9, alpha 1.8, alpha 1.7. Then here I want to compute it so that I can see the results. I want to see the impact of alpha. I want to see the impact of alpha. So I have processed 4 times. Alpha equals to 2, alpha equals to 1.9, 1.8, 1.7. So after computing, then I save it. So now I will load it and let's do the simulation. So let's see. So I have to change the directory because I'm not the current directory. So you can see the system. Can you see the screen? Hello?
Yes,
Your,
sir.
yes, yes.
Can you see it?
Yes, it's visible.
Yeah, so this is the system. And I'm trying to zoom it. You can see this is alpha equals to 2. The time is 1,000. 1,000 iterations, you can see. And then you can see for alpha equals to 1.7. See, the model is showing some behavior that it means that there is impact of this parameter on the system. So what is the parameter talking about? The parameter is talking about the complexity of the media or the medium within which the variables are operating. That is the medium that the variables are operating. So if the delay is much, or the impact is 1.7, it means the diffusion will not be fast. You can see here 1.7, 1.8, and then we have 1.9 here. Here is the normal 2. So if we want, we can change the plots to see what happens when it was 200 only times 200. Let's see. At 200, let's see. Yes, at 200, this is how it was. You can see the system at time 200. You can see the system was little, the diffusion was little, but you can see that at 1.7, the system was behaving differently. As we go to 1.8, you can see 1.9, and this is 2. So we can go on and on to check. Let's check 400. I can change 200 to 400 here. You can see. So the significance is that I've computed all of this and I have saved all the variables. So any form of analysis or simulations or numerical experimentation will not be difficult because I will not take much time to recompute it back. So I have computed it, I've saved it. So it's not easy for me to run the analysis or the simulation to know the behavior of the system with respect to time. You can see from here. You can see. So that is one system. Another system that I want to, that we have discussed, another system we have discussed is, we have discussed this one. So I want us to look at the MATLAB codes for it. So can you see me? Can you see the screen?
Actually, your presentation is fridge right now.
Huh?
No, it's not visible actually. Yeah. Slide
Have you
number
seen it now?
slide number 52 is visible now.
Okay. So let me go to I was trying to say that I will let us try to simulate this in MATLAB also to see. So in MATLAB, I've computed the system also the way I've explained. These are the parameters. And this is also the special parameter, which is alpha. And then the coefficients are here. So this is where we have run the calculations. We have saved it here with this name. And the other part, these initial conditions, the right-hand side. So I've computed it the way I've explained. I saved using .mat. And let us see the simulation. So here I have loaded the variables, and then I will run when t is 200 to see. So when t is 200, you can see this is alpha equals to 2. Can you see it? Hello, sir. Hello.
Sir, 52 slide number is showing only.
Huh?
Slide number 52 is showing.
Have you seen the MATLAB?
No, MATLAB screen is not visible. Please close this present sharing screen and start the MATLAB screen, sir.
Okay, as you close
the presentation and start the MATLAB.
Can you see the MATLAB now?
Yes, it's fine.
Okay, it's all right. So I explained for this system that I have saved, I've computed this, I saved it here. And then now I can load it. So that I can, from there, I'll be able to do the simulation and check the behavior of the system with respect to alpha. So let me run it. Can you see it now? Hello?
Hello? Hello? Hello, Tarusa?
Sir, your MATLAB screen is visible. No issue. Please proceed.
Okay. It's all right. So you can see the MATLAB, you can see the plots. This is for time equals to 200. This is alpha equals to 2, alpha 1.9, 1.7, and 1.5. So we can change it to 400. Can change it to 400. So if we change it to 400, you see that the system has also changed. That has changed.
Sir, sorry,
1.9.
Again, sorry to disturb you, but your plot screen is not visible. Your mad plotters are not visible. If you are plotting something, then it is not visible actually.
Can you see it now?
Yes, Sam's screen is visible again.
Okay, you have seen it. You have seen the laptop. I mean the MATLAB.
Yeah. Your cursor is showing right now. No issue. I am showing. Yes, it's visible. Your MATLAB
Okay.
screen is visible.
So this is the plot. Have you seen the plot?
No.
You have not seen the plot?
No, your only one command window is showing. We are not able to see your plots. And what you are doing in MATLAB right now, it's not showing actually. I think you have given permission to share. Yeah, now it's visible. Yes.
Okay, it's now is visible now,
Yeah.
isn't it?
Yeah, it's visible perfectly.
Okay, it's all right. So this is the plot. You can see this is for t, for time is time 400. This is alpha 2, alpha 1.9, and then we have 1.7, 1.5. So we go to another plot. Let's see 600 times 600. You can see so right. 600 is showing. Can you see it?
Yes, it's visible.
It's all right. So you can see as we progress, you can see the system is changing, and the alpha also is affecting. This is alpha equals to 2. So once you change the alpha, you discover that the system, the behavior of the system, the diffusion, the patterns will also change. So quickly, last but not the least, we change it to 1000. 1000, and let's see. So you can see it's 1000 now. Alpha equals to 2. Then alpha equals to 1.9, 1.7, and then 1.5. The reason why we take time to check these things is to say that this system is dependent
not only on the parameters, but also on the environment. Majority of the systems that we model today, if you want to include other aspects that has to do with complexity of the environment, you have to include fractional partial differential equations into those systems. So we have shown for this system, and for the other system, like I've said, this system also, you can see is the other system. You can see clearly that the gray system has also been affected. You can see that once alpha is changed, the dynamics of the system will also change. The behavior of the system will also change. So let me quickly go to other system, the one that we spoke about. Well, I want to look at the fractional ordinary differential equation, the one that we spoke first. Let me just run the Lorentz system. I'll change the folder. Once I change the folder, you can see this is the plot that we saw. Can you see the plots?
Yes, it's
Hello?
visible. Yes, yes, visible.
It's all right. So you can see this is the plot that I was talking about. And is the Lorentz system. I want to explain that this, you can see from the system here, this is the step size. Then these are orders of derivative. We have Q1, Q2, and Q3. And then we have the parameters are here, sigma, rho, beta. And then this component here is the binomial coefficients. And this we have coded it. Then if you come to the system, you discover that here, these are initial conditions, but this is where we have simulated the system. So here you see a function that we have created, memo, that is a memory component, which we have shown in the order in the slide. And the code is here. Okay, this is the memory component. You can see it has been coded here. So the component is coded, and it's also dependent on the binomial coefficients C1, C2, C3. So with the binomial coefficients, you can calculate the memory effects of each and every one of the equations. So we have for equation 1, equation 2, we have 2. Then we have equation 3, we have the third one here, you can see. So this component is just for us to save the system, save the equation, and then we plot it. So I'll take a look at another system, the one that we discussed before. So here, let me just, I will comment a comment of this, and then since we have used this one, let us comment this one, and then let us look at the voter, comment this one too. So we're left with only one here. Let's see what is going on. It's running. You can see this is the system. You can see this is the plot of the system. And you can see the parameters are here, are given. You can see the constants, initial conditions are given. That is a plot. Plot is given to us, is showing to us here on the screen, you can see. So this is very beautiful. You can play with them, you can change. If we come back to change the initial condition, I mean the order here, maybe 1. If we change it to 1, that is normal system. You can see a different result. You can see the result is there. You can see that if you put them side by side, you can see the differences. So let's go to another system. Last but not the least, let me look at this here. So I now have to run this. Let's see. The last fractional ordinary differential equation, the one that we treated. Okay. There's something that we're supposed to comment. Okay, we have commented it. Let's see. It's running. Yes, it has shown the results. It's okay. The result is shown. This is the result. Now you can change. You can plot. You can plot this to y against x and see whether it's going to give you a very good result. Let's see. It's running. So it has given us this result. You can see this is the result that it has given us. Some is very good. Well, let's try one more. Try this. Remove the comments. And then we plot. Let's see whether it will give us good results also. It's running. Let's see. It has given us these results. result is good. So you can also change to check. Can change a lot of things. You plot y3 against y1. Do a lot of things. You experiment to see their relationship. Experiment is part of it, so that you can see what is going on. So this is the system that's come. You can see that's showing us the chaotic nature of the system. You can plot y2 against y3. You can see. Let's see whether it gives something different. Can you hear me?
Yes, no issue.
All right. You can see now the system is has given us picture. This is looking very beautiful. So we've been able to look at a number of things. Particularly, initially the system was trying to, because of the MATLAB was heavy, but now we thank God because it's working. So I will just give a brief look at some issues in MATLAB. MATLAB itself, if you look at the documentation, you can see a number of things that you see. So the MATLAB is online. It's not free, you can buy, and it's very good tool for scientists and engineers. So see, these are the things that when you open MATLAB, when you launch it, this is the first thing that you see. These are just little syntax about MATLAB you can see here. So you can go to documentation to check. If you go to documentation, you see that MATLAB has a lot of applications. Are you seeing the screen? Hello? Hello, sir? Hello, sir? Hello? Hello? Hello, sir? Hello?
Yes, audible. You are audible.
Okay. It's all right. So I was trying to say that MATLAB has a lot of things that you can check for applications online. You can check them, and I'm trying to share what I want to share with you. Can you see my screen?
No, it's not visible.
Okay, let me just try to. Okay.
Can you see the screen now? Hello? Hello, sir?
Yes,
Hello?
yes, it's visible.
Okay, so you can see that MATLAB has a lot of applications.
Can you hear me?
Yes, can you hear me?
Yes. Actually, the time is about to over, so please wind up within 5 minutes because we have to take the question answer session as well.
Okay,
Please
it's all right.
please try to finish within 5 minutes.
I'm about to summarize.
Okay, thank you.
So if you go to the web, you can see that MATLAB has a lot of applications. Then from AI, data science, statistics, mathematics, optimization, signal processing, a lot of things. So you can take a look at it. And also there are some other applications that are available that are developed by MATLAB. So take a look at them. If you have any issue, you can contact me or anybody that you feel that can be of help with for that kind of solution. So thank you so much. I do appreciate every one of you for listening to me. I also apologize that the network, the system was having 1 or 2 issues, but at the end, it responded. So thank you so much. Can you hear me?
Yes, Professor, it's audible.
Thank you so much. I've just summarized, I've just concluded. I want to thank you, thank the head of department, and thank everybody for coming, and also apologize for the mix-up, the technical issues that we had. Thank you so much.
Thank you very much, Professor Shikha Samuel. Now we are moving forward for the question answer session. There's one question, Professor Shikha Samuel. How can we, is it possible to solve the higher order non-linear differential equations, basically pertaining to the Navier-Stokes equation of fluid dynamics?
Yes, is very important. I mean, it's very easy to solve, particularly because using spectral methods, you can convert partial differential equations into ordinary differential equations. It becomes very easy to solve, and the coding is very easy also. So it's possible.
Okay, so you mean that all the computational fluid dynamics related problem may be easily solvable with the help of MATLAB?
Yes, sir. Yes, sir. It can be solved easily by MATLAB, and there are so many packages and codes that are available for solutions, Navier-Stokes equations, and other fluid dynamics systems.
Yeah, but I think there is a one drawback that it's not open source software. That's why. So people have to buy it.
Right, that is like, there are so many other softwares, like you can go, Python is there. It has so many libraries. You can use Python. Python is very vast. You can use other Julia and other programming languages.
Okay, thank you so much for accepting our invitation. Thank you so much.
Professor Samuel, thank you so much. And I would request all the participants to please switch on your video cam for a while so that we can take a screenshot.
Okay.
I request all the participants to switch on your video cam. The session was very good, Mr. Samuel. Some technical issues were there at the beginning, but later on it was good. So thank you so much for accepting our invitation and give us time.
Thank you. I appreciate it.
thanks all the participants as well
pleasure.
to have patience. Okay, just a second, I'm taking. It's captured. Thank you so much, all of you. And we will again meet tomorrow at the same time with a new session. Thank you so much. Have a good day.